Testing, yeah? Okay, good. Oh, I'm going to have to wear my sunglasses for this because the lights are right on me and I'm not a stage actor. So, welcome to Saga. I'm David Beberman, the CTO, and we're going to talk a little bit about SagaPython, which is our programming language for the SagaChain for scalable blockchain technology. Before we start, I do have to say I've never walked through these slides before, so probably will stumble a little bit. You're seeing it live as it's going. Okay. Next slide. I hope they are. Unfortunately, I can't see the slides myself, so hopefully they're doing. So SagaChain motivation. The SagaPython, in order for SagaPython to make sense, I need to walk through some of the motivation of why we're doing SagaChain. So I'm doing a little bit of intro of SagaChain first, then we'll do a little bit of a quick overview of what Python is for people who aren't familiar with it, go through some discussions of our class-based system and how that evolves to SagaPython. Next slide. So the general issue in blockchain technology for scalability is what's known as the Trilemma. This has been very well discussed in publicly. You can find articles on Medium about it. In fact, that is I grabbed the diagram off of a Medium article. That's not ours. The idea is that in the triangle of security, decentralization, and scalability, if you push on any one side, the other sides have to give. So if I increase my scalability, I have to decrease my decentralization. If I increase my decentralization, it'll pull my security and scalability together, and so to speak. What we're doing is saying we want to rethink this specific thing. And what we're doing is looking at scalability from the point of view of capacity. And what I mean by that is the number of transactions that can go through the chain at any time goes up with the number of nodes that are operating the chain. So to give a quick background, obviously everybody's using Bitcoin. Bitcoin's a great technology, but even though there's 10,000, 20,000, 30,000 nodes mining it, validating it, it runs 10-minute blocks. Doesn't matter how many nodes are running. If you had 100 nodes or 10,000 nodes, it's still going to have the same throughput. If you look at Ethereum 1.0, it's doing the same thing. Now we've addressed a lot of that with layer 2 technologies, but layer 1 technologies have pretty much stagnated at that. It's not a bad thing, it's just that we want to do better than that in layer 1. So what we want to do is parallelization of execution would be execution sharding as opposed to straight data sharding. In order to do that for us, what we've decided to do is increase scalability in that, walk through parallelization. But what it'll do is we won't decrease the decentralization or decrease the security, but we won't necessarily increase it. So you'll get more scalability with the same amount of security. As long as you're above, it's still these classic 50% plus one attack will attack us just as much as anybody else. But the opportunity to attack it is essentially constant, rather than reducing as you increase your scalability. And that's basically our core. In the end, that's the core thing that we want out of it. Okay, and it says at the bottom. Okay, next slide. So, in order to do scale by parallelization of transactions, you have to have a way to distribute data across shards. Now, even in the database world, they do exactly the same thing if you have a distributed database. In order to do that, you have to have some way to handle the distributed data. Now, an Oracle database, for example, will do record locking, or Postgres, or one of them will do distributed record locking. Remember that they all are talking to each other with guaranteed code, so they don't have a trustless problem. They're a trusted environment. We need to do it as a trustless environment. And we still need to guarantee that the next bullet says guaranteed determinism. That means that once you execute the transactions on any node, all the other nodes will do the same way, and it's called replicated state machine capability. That's a standard problem. The core problem then is to solve how to synchronize the state replication through a replicating state machine, which is what all these actually are, such that you can do the transactions in parallel on multiple shards. If I can then, you'll see later, if I can then increase the number of shards with capacity, then if each shard has X amount of transactions per unit time, then you get capacity increase times the number of shards. But that only works if there's a way to do them in parallel. And that's all of this, all we're doing, everything about it, is to figure out how to solve that one problem. Next slide. Okay, so in the ideal situation, you have very little cross-shard communication. So I need to back up one. Generally, in smart contract communication today, the idea is that you do cross-shard communication for any of the data that you need, or cross-chain communication as well. Nothing wrong with that, but there's a couple caveats. It's hard to make sure that it's guaranteed secure. But also there's an issue of just straight latency. If I'm executing a smart contract that needs data from another smart contract, I've got to stop and go get that data from the other smart contract, and so on. That extends. The problem with that is that somewhere along the line, that cross-shard or cross-chain communication requires overhead, which increases the latency of the transactions. So you end up with something that the more cross-communication you have, the more latency engenders. So the idea, of course, is how do you minimize the cross-shard or cross-chain data requirements? Okay? And the other one is, of course, then in our ideal situation, as I've said, the number of shards can increase with a number of nodes. And of course, as a chain gets more popular, more people will run validators in miners. So if they're doing that, we want to take advantage of that to also increase the capacity of the chain. And so, next slide. The core motivating technology that I looked at was called conflict-free replicated data types, CRDT. There's a great paper on it. You can read all about it. Its design, though, was slightly different than the way we went about it. So in a CRDT, generally you could do things like unordered transactions. Very classic, think of adding and subtracting. If I have a list of additions and subtractions, the end balance is the same no matter what. And you got to remember to shut your cell phone off. Hang on, whatever, it'll call a couple times. So that doesn't quite work in a blockchain for a financial model, because if you have an ordering of the transactions that takes the balance negative temporarily, that would be a bad thing, even if the end result is correct. So we don't really want that type of capability. So I can't have completely unordered transactions for types, but I can take the model concept of separating the data such that I have independent data that can be executed on separate parallel chains. So the organizing principle, the core way that we go about doing that, is all I'm trying to motivate how we got here rather because the whole point of SagaPython is not going to make a lot of sense without it, is that we looked at the blockchain state as an object state database. And I'll talk about accounts in a second. In fact, if you look at even Ethereum, it is actually an object state database. It only has two types of objects, though. One of them is your regular account. The other one is a smart contract. There's no implicit typing information in those objects, and there's no inheritance to it. So we look at it as an object state database, but then we use an account model as an object organization principle. And what that allows us to do is the second line there. It allows us to guarantee a very important piece. For a subset of the database, we can guarantee that the objects that are modified are only modified on one shard at a time. So that means that I might have multiple shards modifying different data where none of that data is, of course, related to each other, and so there's no issue of order of transactions between them. And that's one of the key points that if you can pull that off, you can then scale your blockchain. One of the ways I explain that is real simply, if you have transactions A to B, Alice to Bob, and Charlie to, I don't know, Danielle, if they're not related to each other, I can do those completely in parallel, transaction A to B and transaction C to D. If they do have dependencies between them, then they need to be ordered. And so we followed that's the motivation of CRDT is how we get there. By the way, can they ask us questions on streaming at all? No? Okay. All right. So the only other motivation requirement we have for this is that it's a completely open system. What I mean by that is we're going to publish our code. There's nothing proprietary about it. And there's nothing in the design of the blockchain protocol that is specific to our code. So it's perfectly possible to re-implement an entirely different language, an entirely different system, provided that you follow the rules of the protocol between the nodes. Okay. I think I basically said the second part. All protocols independent of specific software implementations. We are actually implementing the node software with Golang, and our current programming language for it is SagaPython. But even there, it's possible to, although theoretically we haven't done it yet, actually run a multi-language environment for the environment as well. Okay. I'm going to kill myself on this. All right, so make sure I'm in the next slide. The next slide should be blue, introducing the object state database. Yes? Okay, good. All right. So what I'm going to do is I'm going to describe a little bit of the object state database and the class manager infrastructure that manages the object state database. Okay, so I'm building up to showing the source code of SagaPython and how that works in context. If I show it out of context, it's like, okay, it kind of looks like Python and won't make a lot of sense. So next slide. Before we go anywhere, this is very, very basic. Just wanted to make sure that there's no misunderstanding. Hang on one second, my stupid. Come on. View. There we go. It's a very simple, just like every other model. You have a client, either on your cell phone or on a laptop or any type of thing, and it's submitting transactions to the network. When it submits it to them, the node, one or more nodes, see the transactions. We're not going to go into the details of the consensus algorithms for this talk. That's entirely another discussion. But it receives the transaction script, which is SagaPython code, and it executes it inside of what is actually a Python program. And the other piece of it is that it interacts with the object state database, written here as the blockchain database process. If anybody wants details, I'm actually using LevelDB as the database internally at the moment. Okay. So could go to the next slide, please? All right. So quick background on terms, so we can get into this a bit. When I'm saying class manager infrastructure, that's our system, and I'll say CMI a lot, for managing and creating a class concept on the blockchain. I'll go through some slides that diagram that out and what it actually means in a minute. The next one, CMI object, means that there's different viewpoints. There's SagaPython's viewpoint, there's a consensus viewpoint, there's a class manager infrastructure viewpoint of what an object is. So I'll walk through different viewpoints. It's just so when I'm using these words, what they mean. SagaPython itself is the modified Python environment. There's very little difference in the actual compiler and interpreter of Python and SagaPython. Most of it is using it, and the way we use it is non-standard. There is a minor change with the because we're going to use the concept of gas units, so the main loop of the interpreter, we add a counter for the amount of bytes used. So the next one, a SagaPython object, is one more level up of viewpoints of an object from the SagaPython view versus a class manager infrastructure view versus a consensus view. And again, I'll show you a diagram of it. The Python object, distinguishing it from SagaPython, is that we support the idea of running regular Python code inside of the class manager classes that are running SagaPython. And that's a little confusing. It means that we're actually running two class models, one inside the other, and essentially two different versions of the same language simultaneously. So it's a little confusing, but when you see the code, it should be relatively easy to grasp. A Saga class is a CMI class. I'll explain the object environment in a minute. That is Saga defined by SagaPython. The class obj_var, or class object variable, is the class that represents CMI objects to SagaPython. And everything in this is objects. You'll hear me say object way too many times. The Saga class method is the method call on the CMI object that a SagaPython code will actually call, and then a field is something that can be, updated, read, that type of thing. Okay, next slide. So, for us, the object state database, basically the consensus algorithm's entire job is to make sure that the object state database is up to date on all the nodes. The object state database is that every single object is referenced by a unique ID, we call it an object ID. And in our environment right now, it's a 256-bit key based on SHA 256. So what you do is you're guaranteed that every object is globally unique forever. Doesn't matter where it came from, whatever, it's stored. It's either stored on the blockchain temporarily or completely. There's persistence maintained in it. But the key point is that from the consensus viewpoint, all it really knows is that I've got an unstructured array of data referenced by an object ID, and my entire job is to make sure that that unstructured set of data is constant across all of the shards when it's needed. The next level up is above it, which is outside the knowledge of the consensus algorithms of SagaChain altogether, is the class manager infrastructure. And so the diagram here is showing that from the class manager infrastructure point of view, instead of being unstructured data, it is in fact a property table, and it's indexed by the properties are indexed by known indexes. So So the class manager needs to grab a little quick water. So the class manager superimposes on top of the consensus model a property table, so that when it's as the next slide show for the object system, that the properties are something that can be retrieved and set independently. Oops, that's farther down. Okay, next slide. So it should say object state database replication consensus viewpoint. So I'll leave this up here for a second. One of the key points is the second bullet on this slide, which is that the object state database is strictly maintained by the transactions. This is independent of us. Every replicated state machine environment does the same thing. The only difference for us is that our code and our system is flexible based on class code. So I'll get a slide farther on, but I'll say one thing really important. For us, all code that's being executed in a transaction is either inside a transaction script or it's being pulled off of the blockchain from other classes. So it's inherited code. This is important. There is no local code. There is no individual, like in a smart contract where the code is pulled into it, each one separately. We don't do anything like that. All our code's on the chain. So I think I just went over this, but I'll say it one more time. All the objects, as it said, are global 256-bit keyed objects, so that essentially you'll never run out of keys. And that from the consensus viewpoint, its entire job is to make sure that think of it as blobs of data, are in fact replicated everywhere based on the blockchain transactions. And again, this is very fundamental. From the database class manager, object state database class manager infrastructure viewpoint, the CMI, is that each object consists of properties, as we just discussed. But here's where things get a little interesting. The first property of every object, always, is the type of the object. Well, the type of the object, also known as a class, is nothing more than another object. That just happens to be a class object. And by the way, you can make a meta class by having the class object have the type of another class and so on, and we actually do a meta model and a meta-meta model and actually a meta-meta-meta model to actually make it work, but that's details that are internal to it. Because the classes are objects in the state database and because they have the same secure hash unique IDs, the classes are maintained by the consensus algorithm without it even knowing that it knows no difference between the classes, the objects, or anything like that. All the method code for a class. So in a object-oriented system, you send a message to an object. The message is resolved to the method in the class, and it's called with the instance data of the object. And we do exactly the same thing. A key point is that all of our code is then stored in the blockchain with the class, which means that when you go to execute a method, you're going to take that code and you're going to pull it out of the blockchain transparently. The CMI does this for you. And then it's going to run it. Well, what we're doing, though, for readability is putting all the source code for the methods in the blockchain. And then each node locally can pull it out, compile it, and execute it. And as I'll show later, Python's the perfect environment to do that with. There's another little hidden advantage that we went with, which was kind of something that fell out of this, not our original ideas, is that a class has multiple object instances. So one of the classic things is we have a class account. So every account instance is actually referencing the same piece of code. So you don't have multiple copies of the code on the blockchain. You have one copy of it, and everybody's referencing it. And the same thing if you're inheriting, then I have a class that inherits from a class and so on. I'm using the same code over and over and over again, and essentially the size of the code becomes immaterial to the blockchain, which is a really nice little feature. Oh, I think I just covered inheritance. Okay, so let's go take a look at it diagrammatically. Next slide. I'm going to take my glasses off to read my own thing here. So what I was just trying to explain is trying to be shown here. If you look on the bottom right, is that your right? Yeah, bottom right. The basic idea of an object instance is that it has a property table and it has properties that are managed by its class. It also, the first thing it does in the first field references the class object, and the class object defines the methods and fields and instance data for it. The other thing, though, is that in our environment, we did multiple inheritance. That means that a class can inherit from more than one class. This mirrors Python's model as well. They do the same thing. We actually use the exact same algorithm. It's called C3. There's a paper on it. And the short term is they call it Method Resolution Order, MRO. So our MRO on the class side for the CMI mirrors the MRO on the Python side. That allows us to do, it makes it so that when you're writing the Python code, you can do local multiple inheritance, and then you'll get the same feeling when you're doing the class inheritance across the blockchain itself. Next slide. So this is the SagaPython viewpoint I was saying. And if you look at the objects instance down the right side, what you'll see is that, and by the way, it only shows single inheritance, but obviously it could be multiple inheritance, and it would be linearized and still look the same. Each one of the classes adds its own instance data to the object instance. So when you're executing a method in one of the classes, it's using its instance data. Now this is standard object-oriented technology. You know, basically, anything from C++ on is doing this. But the difference is we're doing this on the blockchain. These are all persistent objects. So it's kind of like they're always running all the time, full-time, everywhere. In the background, we're pulling them in and out of a database, obviously, because you can't keep them all in memory. But it logically feels like it's one giant address space. Yeah, I think I'm good with that. Okay, next slide. Cool. Okay. Actually, how long have we been? 40 minutes? Okay, good. So let's go down to the core piece. Hang on, let me make sure I get the slides right. I had one out of order earlier. 1 second. Yeah, I do. That all happened. Oh. There we go. So we should on a blue side account model in global invariant. So this is the core piece that enables what we're just trying to say. We want to reach sharding. We want to be able to have separated data. And the account model is the core piece that makes that possible. So let's dig into it a little bit. So our primary model is everything when you talk to an account is that there's a single account object. You create an account. You have an account object. You have an object ID for the account. The account object can, quote, own other objects. And what that means is it has a reference to another object. One of the requirements is that every object can only be owned by one account at a time. So that means that if I want to know that all of the state of my account is somewhere, like on a particular, being executed on a particular shard, all I really need to do is follow all of the references to all of the objects that that account manages. This is actually known as an instant containment tree. And so we follow we create an instance containment tree model for every individual account. Because of that, we can create an invariant that says that you will only ever modify an account object or any of its children objects on one shard at a time. You don't have to worry anything about it. We're doing this in the background, but it means that I can have, as long as an account is, as long as the accounts that are involved in a transaction are separate from other accounts involved in another transaction, I can put them anywhere I want. They're not tied to any particular shard at all. However, as you notice the next line down in invariants, the only way that this works is if at the time that you're executing that transaction on those accounts, that those accounts have all of their data up to date globally. What's interesting though is if you invert that statement, it means that at any other time, we don't really care whether any particular nodes on any particular shard have up to date data on those accounts. That does a really interesting thing, which it actually, actually I think I have it farther down, so I'll wait for the next line there later. What this does though is you then have our entire model is nothing more than trying to figure out how to negotiate the ownership of an account on a shard. So a shard, when it's executing an account, essentially has ownership of that account in all its objects. So your entire protocol, your entire consensus, everything about everything we're doing is just to make that possible. Account ownership, not object state, blah, 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 blah. Oh, right. So there's one other really important piece. What this also means is that when it comes to negotiating account ownership, we're not actually negotiating, we're not moving the data at that time. So this isn't cross-chain communication, it's not cross-shard communication at all. All we need to do is negotiate who owns what. If it turns out that the account's not up to date on a particular shard, it has to go get that data. But it's completely separate, which means that most of the time you gossip to all of the nodes across the entire blockchain, all of the updates. So most likely, you will either be running a transaction on an account that you've already owned as a shard, you being the programming language, not you personally, or you're starting a transaction on an account that is already globally up to date because of gossiping. So most of the time, there is no cross-shard communication whatsoever. That's really key for scalability. So there's a little bit, we weren't going to go into the details of how we do that a bit because that is in itself a entire conversation around consensus protocols. But what does have to happen is that the ownership of the accounts do need to be negotiated. And so what I did is just a quick little dig down into this. Every account, it can be in any one of the states of currently owned by a shard, completely unknown, nobody's processing it at all, or it can be in transition from one account to another. I think I just said this in the last slide, apologies. Okay, I guess that's from downstairs, background noise. The account ownership is the important thing, not the object state. And I actually jumped this slide, but the idea is that the individual shards execute the transactions, update the object state database locally. To when they execute the transactions, they put them in blocks normally, and then they're gossiping those blocks to all the other nodes in the entire blockchain. So that means that at any time, every single shard, when it generates a block, gossips it out so that at some point, eventually, all the nodes have all of the data and they're all up to date. But it's, as I said, it's a lazy type update. The last thing on this slide is a really extra thing that comes out of nowhere, is that if I can decide, or the programs can decide, where the accounts are going to execute, and we have a list of transactions for accounts, you can do look ahead of the transaction list and decide which shards to put the accounts on. Well, that allows you to load balance across all the shards. See, one of the problems with an environment like a smart contract environment is they tend to be tied to a single shard. So if I have a smart contract that's seeing a lot of load, it's still only going to go as fast as that individual shard. In this environment, if all of my accounts are in fact independent of each other, and I have independent transactions, I can load balance across all available shards. So what's nice about that is, as I again increase the number of shards, I increase the opportunity for load balancing. Okay. All right. You'll give me a second to have some water? So that's the motivation, a little closer. So that's the motivation behind why we're doing SagaChain, what we need to be able to accomplish, how it scales essentially without going into the details of any of the protocols involved, and the fundamental invariants that we're going after, that an account is only executing on any one shard at any one time. So the point of all of this from here on in is, what programming language do we use? If you look at Ethereum, for example, they're running their own bytecode interpreter with Solidity, and there are other languages that can compile to it. Excuse me. There are other languages out there. Some people are implementing Rust and those types of things. Python is a nice open source, very well established. I'm going to say that the first release was either 1989 or 1990. Very highly evolved language. The nice part about it, though, it is also completely dynamic. It means that you can compile and execute code on the fly. It means you can essentially do what's called data modifiable code. It means that I can create what looks like a string of data, send it to the compiler, and then execute that code. The reason why that's really useful for us is our methods are actually source code. We compile them on the fly and execute them. Okay, so next slide. Sean, Python programming language. White slide. Yes? Good, okay. So, what is Python? I literally pulled this off of the python.org website. If you want details about it, please go and visit python.org. Because it's an interpreted language, bytecodes are interpreted languages. You compile the bytecodes and interpret them. We take full advantage of that across the board. And I just pulled up a handful of companies. Python's been used, heavily everywhere. It's a very, very stable environment. What we do with it is a very slight modification to it, and fundamentally it is Python. The way that we use it, though, of course, although it looks like Python code, tastes like Python code, we're doing a lot of, let's call it magic in the background. Okay, next slide. What I did is just threw in for basically couple quick pieces of fragments of code just to say, yes, this is regular code and we use this type of code. On the left side, defining a function, defining a class, calling a function, right side a little control flow. All those things are standard things you'd expect out of any programming language. One of the Python specific things inside of Python, everything is an object. It's a little while to it's hard to get used to that, but it means that you can pretty much assign anything to anything. It's a dynamic typed, late dynamically typed language. I think I have a slide that says another piece in here. Do I? 1 minute. Good. Next slide, please. So at the very highest level, this is how we use Python in SagaPython. First part is that we're still using full Python syntax. We have not modified the compiler, we've not modified the interpreter, with one exception. In the top of the main loop of the interpreter, we have a byte counter so we can generate gas. The standard Python doesn't do that, of course. We do restrict the environment, and I talk about that at the end of the slides. Essentially, Python itself is designed to be a full system-level programming environment, talking to your OS and all those types of things, and that's not a good thing for distributing code across unknown, trustless nodes. So we take all that out. The next point is because Python can compile and interpret code dynamically, it gives us the ability to load the code onto the blockchain itself rather than having to compile it offline and do it. So in a sense, Ethereum, for example, does very similar. Each Ethereum smart contract compiles its code while they compile it offline with the bytecode on, and then they're executing the bytecode essentially dynamically. The difference is, and you can also call libraries and that type of thing with it. The difference here is that it's formalized into classes and objects. Yeah, going to the next one. No, don't change slides, sorry. I just need to read my own notes out of space here. Right, so one of the interesting things about Python, it marries three different concepts: procedural level programming, functional level programming, and object-oriented programming. Now, because of that, we're able to do some really interesting things using the functional programming overlaid over the object-oriented programming of it. And I'll show a couple of the pieces of code in a little bit. And I think and by the way, it's stored in the object state database if you haven't heard me say that yet. Okay, next slide, please. Oof. Okay, so what I did was write out from the very beginning, let's keep it as simple as possible. You write a transcript. Sorry, you write a transaction script. Somehow that came out as transcript. Write a transaction script. You run it through a tool to submit it to your client at this point. And the client, of course, could be on a node just as easily as on a separate machine. You submit it to the blockchain. In this case, I reference it as submitting it to a single node, but you obviously can send it to multiple nodes because transactions can be sent anywhere. The nodes call the SagaPython execution app to actually run it. And it does the execution, and you get the update of it and the consensus on the object state and all those types of things. But literally what we're talking about is a system that takes source code on a script, runs it through a submission tool, sends it to the blockchain then executes that code. And want to be very clear about in case, just make sure everybody understands it. Next slide. This gives you a very detailed look at it, and I have to take my glasses off to see it. So what happens bit by bit, I'm just going to walk through this real quickly, and then I have a second slide on it. So assuming that you were writing your transactions by hand, which is the way like we originally wrote Bitcoin scripts without any apps or anything like that, you would write a script, we're going to go through the syntax of it. You run it through a tool that does a little bit of pre-processing and creates a submission for the blockchain. You send it over the network to nodes just like anybody else. Transaction gets executed. Consensus gets reached on the block that contains those transactions. The object state database gets updated. And then the interesting thing is the classic results. The results are logged into the block just like any other blockchain does the same thing. So fundamentally, it looks the same in the end, conceptually, which makes a lot of sense if we want to make a viable blockchain. Next slide. The next slide just says, look, I've got the exact same thing. The only difference is I have applications that automatically generate my transaction scripts for me. And therefore, you can go right into any type of model that runs anything on a cell phone, any type of app you feel like. And so the only difference is in the top left, it's a D app instead of an editor. And the next slide. How are we doing? So I'm not going to walk through the details of this slide. The key thing is that if you're writing a transaction script and you're going to submit it, you're going to submit it with gas. And if you fail, if it has an error, it's going to consume the gas, but no state happened, and basically it's a complete failure. So because it's an object state database and you can read it, you can have the clients actually reach out to the blockchain and simulate the entire execution. So on the far left is, I think I'm going to go test my transaction before I actually submit it. And that's what that's all about. The rest of this is just following through the tools that actually make it happen. I'm not going to walk through this slide. But that's a really important point, is that we create a tool that allows you to avoid throwing away your gas trying to get the transactions to run. Next slide. So you good? Okay. So there are two command line tools that we use with SagaPython. I'm going to walk through them real quickly. There's not, I think you've already heard them. So next slide. That'll be the SP for SagaPython submit. And what happens is, from the command line, you would call this tool to generate and you'd hand it a transaction script, and then it would go and obviously submit this. Walking through a couple of things, and you'll see later how it's done, but first of all, if you're going to submit a transaction, you need to be able to sign it to verify who you are. You're signing against your own account, which is on the blockchain, which has a public key in it when you created the account. your, the next piece down is about private keys. Don't worry about the tuples. You can add anything you want there. As I'll show farther down, it's perfectly possible to add keys for other accounts that you want to send messages to. So by default, if you sign a transaction script with your account, you can send any message to any object in your own account. Okay? In limited situations, you can also send transactions to objects in other accounts. However, you also want to be able to control whether or not you're authorized to send a message, I'm using the wrong word, a message to an account, another account from within your transaction script. So to do that, you need private keys. That's what the next entry is. The next one beyond that is just defining variables that get added to your transaction script, and I have an example of that coming. And then if you want to just generate the output of it to see what it looks like before submitting, there's obviously a flag to do that. And then it returns the hash of the transaction. So part of what you're doing when you're providing your private keys, you've got to sign against something. What it's doing is taking your transaction script, hashing it, signing that, and adding that to the end of the transaction script to verify it. Next slide. So listening to blockchains is a general capability. We have a SagaPython listen, and you can listen for individual objects, individual accounts. The amount of, I put confirmation count in, that's due to the consensus, how many confirmations of a block that contains your transaction you want to hear, and what the hash value was of the transaction that you were looking for. That's a very straightforward listener. And you can, in our environment, because it's object-oriented, you can actually listen for individual objects within account, changing state, that type of thing. We haven't done it yet, but we probably can even say you could listen for specific fields or specific methods on specific objects that are actually being modified. Or you might be able to listen to an object, an object type, a specific class, across multiple accounts. That type of thing too. A lot of flexibility there. Come on. Okay, next slide would be transaction script overview. And we've been 45 minutes or so. Let me take a couple minutes to have a drink of water. I'll be right back.
Okay, guys, just as a quick for information before we kickstart the next section of the tech discussion. For any developers out there who are interested in winning a little bounty of 50,000 Saga coins, if you go ahead and register on prosaga.io as a developer, then you can get entered into the competition to win some of that stuff. Thanks, guys.
And we're back. Okay. So there's a couple of, before I show you some of the source code, there's a couple key pieces that we use in Python to make SagaPython happen. Actually, I think I don't go into all of it here. I just do one of them. So next slide. It should be on SagaPython Decorator syntax. So to create a class, a CMI class, a class manager infrastructure class in SagaPython, we use a decorator, which is a function in Python. And you put that in front of the class definition. I'll show you that source code in a minute. And you put all the information you need inside of that, which includes the inheritance, which is called base class list, a meta class, which would be a CMI meta class, not a Python meta class, the account value, OID, name, etc. If you go to the next slide, please. I'm going to go a little bit faster because time-wise. What I do, and I believe that, I'm sure the slides will be available online. So in this environment, the meta class is on the objects in the CMI, not Python. So the meta class would be a class that creates classes, and we use that very heavily, and you can define new meta classes. The account normally is the current account of the transaction script, but in certain cases it's possible to say I want to create this class in a different account. In general also, in general it's not really interesting to have classes in your own account, and there's a global account for it. So the object ID is that SHA-256, SHA-256 value, and normally you would not specify it because the environment should return it back to you. It is also possible to specify it, and we take advantage of that, of course, to build in some foundation classes. Generally, you would not name your class either with a string name. All that you're referencing off of the IDs, not names, but we do have a global object name dictionary. Not going into details, but there's a reason why in general you don't want to name things in terms of performance. When you try to name a class or any other global name, it causes the entire blockchain and all the shards to synchronize, and so that's a bad thing. It obviously slows everything down. So in general, don't do that. The last piece, which gets into a really interesting thing, is that in general, in a programming environment, you compile your code locally, you import or include various modules, and then you compile it and submit it to, in this case, so Solidity, you'd submit it to a blockchain. In other cases, you just run it. We don't allow anything to come locally out of your system whatsoever. So what we're doing instead, because we still want to be able to import code, is we enable importing modules, Python modules, from other classes on the blockchain. And that's it's very important to understand the difference between that and inheritance. It means that I have a class, a CMI class, written in SagaPython, but it can now call Python functions that it included and imported for itself, but those are local to that individual class and that in an object instance for that class. Takes a little while to get used to that concept of marrying the two models together, and to be honest with you, I haven't come up with a really great way to explain it yet. Okay. Next slide. Should be SagaPython key syntax concepts. I think, do I have the slide names wrong? No, I'm backwards, sorry. Ah! Oh no, I put the two names wrong. Great. Or am I? No, I'm sorry, it's me. No, that's my wonderful mouse pad that's dying. Sorry. Okay, so now we finally say we've motivated why we're doing this, how we're doing it, what the objects are, those types of things. Now let's go look at some of the code. A lot of build-up, but hopefully it's not anticlimactic, because unfortunately, I mean, it's really not that hard to write afterwards. So next slide, please. So a SagaPython transaction script consists of 3 functions. One of them's a header, one of them's a body, one of them's a tail, and I'll walk through the pieces of it. I use the double underscore just because Python likes double underscores. It doesn't mean anything in particular, but again, if you're a Python developer, the objective is to make this look as much like regular Python code as possible. Although it looks like a single script, it actually isn't. Each one of these functions is compiled separately and executed separately. So you write it as a single script, and it gets run as individual pieces, and there's important reasons why we do that. The header contains the same type of header information, you'll see that farther down, that you would expect out of any transaction submission. The body does the actual transaction execution, and that's, in the end, looks like regular Python code, but integrates transparently with the class manager system. And then the tail, it is actually generated by the SPSubmit tool to generate the hash of the transaction and a signature. Because it's kind of, chicken and egg. You have to actually generate the hash to be able to sign it. So we have you can't do that on your own. Next slide. Okay, so let's walk through a very simple example and start from the beginning. I'm going to do the header, body, and tail. So the header, and I would say that we haven't finalized all our fields yet, but for the moment we have this many. You have the account object ID, which is who you're sending the transaction to, usually the client, and client has to have the private key and has to have passed that in the submit to be able to sign for this account. And the account maps, when you've created the account, maps to whatever public key you've published. The transaction sequence number, so every account maintains ordered sequences so that you don't get replay attacks. The gas units are exactly the same type of gas units that you're used to in all the other blockchain world, and it does count by bytecode. One thing important, I think I say it somewhere else, but the cost for doing the class manager message dispatch is single byte, is single gas unit. So because there's a lot of code that makes that happen, none of that is tied to, you're not paying for it in terms of Saga coin at all. And then the extra gas is actually you're paying the nodes extra transaction fee, that's all. And the next slide. So this is where it happens. This is the body. And what I did here was write out some from the very basic. Literally it's a Python program. And so if you were to just make it do something like calculate pi, you could send it out to the blockchain, and all the nodes would calculate pi. Now, that's a great way to spend all your money if you like, because you're still going to eat up all the gas, but it literally is a programming environment. I wouldn't do that. That's not what it's meant for, but I was trying to get that point across really early. If you look down, so the first point is the general Python. You can see setting a couple variables, x equals 1, a name equals Python test. So the next thing you need to be able to do is send messages to objects. So the way we do that is we create a reference to an object, and you can see that in class obj_var. My apologies, I can't highlight things on the screens. It'd be a lot easier, so I'm going to talk it through. It'll be a little bit disconnected. But you would know the object ID that you want to talk to, and that's part of you as a client writing either as a script or using a DApp, saying I want to send a message to something. The class obj_var is a class that's included in the SagaPython environment, and then once you've done that, you can simply send a message to it, and that's what the next line down is. I'm going to make a method call on that object. The one thing you'll notice from a difference between regular Python and SagaPython is that if you look at the word obj_var, obj_var, there's parentheses after it. The reason for that has to do with returning a proxy stub object, which I actually show a diagram of later if we get to it. Unfortunately, I really wanted to not have those parentheses, but I also didn't want to modify Python, so we'll live with the parentheses for now. In a normal Python environment, if you were calling a method on an object, you would simply use the variable name dot in the method, and in the future, if that turns out to be something people want, we'll obviously modify the Python compiler, Python language to support that. Okay. So one of the interesting parts is because this is a full Python environment, a full programming environment, you literally can write control flow code in here as well. It's not just I'm going to send a message to an object and get the result back. So let me compare that to a smart contract. In a smart contract, you send a message to the smart contract code, and smart contract code executes, whatever happens to be there. In this environment, you not only have the code and the classes, but you can actually have your transaction script do multiple things as well. And so down below that, you'll see there's a straight if statement. It says send a message to a value like obj_var2 here, which is a different object. I'm sorry, I've got this slightly wrong. It's taking the return value of the first message, and it's deciding whether or not to send another message afterwards. In fact, we use that for if you want to do a multi-party data transfer, and you have some source on that as well. And then, obviously, the output of this, any data that you want, you have to log so it gets into the block itself. And so, a really difficult function called log is how we log the data. So not really much you could say about that. One of the key points of this, though, is, as with anybody else, no object state update happens if the transaction does not execute to completion. So if there's an error, or you forcibly error exit out, which is possible to do, the state stays the same, nothing happens. So it's completely atomic. And next slide. And the tail is very straightforward. You all right? Okay, good. The tail is essentially what you do. The code has the fields in it already for the hash and signature, but the values are stand-in because they're completely overwritten. And what it does is it writes in the hash value of the rest of the hashing all of the source of the transaction script, and then signs it using the private key that's passed in from SPSubmit, and then you have a completed transaction ready to be submitted. There's more details, but that's high level. Okay. So let's go do a couple things. Next slide, please. Blech. Next slide, please. Creating a new account. So the first thing you want to be able to do in a blockchain world is create an account so you can use it. And you can write a transaction script to create as many accounts as you feel like, of course. There are some caveats in that if you create an account and it doesn't have any value and it's not used, eventually it will disappear. But those are details that aren't really important right now. Next slide. So the core of a class account has to have the transaction sequence number we were just talking about. You would want it to have a balance of SagaCoin. SagaCoin, of course, runs our blockchain. It's the word lingua franca of our blockchain. Public keys, you can have more than one key and so more than one private public key pair to be able to authenticate against the class account, and actually you can do that for other objects as well within your account. And then child objects that the account object references. That's the whole point of having a containment tree of instances of objects so that we can shard, and this is where it starts. Next slide. So there's one really interesting thing, which is that when you send a message, when you send a transaction script, it always has to be to an account. So how do you send a message to create an account if you have to send the transaction script to an account? So we create a global system account with an account manager that creates accounts for you. And so you can send it to them. The really fun thing about that is because it's a full class, first class object model, meta-class model, you can actually create your own global account managers to create your own accounts as well. Not sure yet what to do with that capability, but it's there. Walking through it, very straightforward. You have the same header as before. The only difference with this particular one is, again, because it's Python code, I can define variables. And actually, I could pass the variables in from the SPSubmit as well with define statements. And you fill out the header, and you return it. I did put a couple points in that in terms of Python code, that's actually a dictionary, or dict, D-I-C-T in Python. That's what's actually being returned. For people, again, I'm trying to make this as standard Python as possible. I'm using a factory model, which means that there's an object called account factory, which is an object instance of class account factory that creates accounts, and it does that by creating instances of class account. So when you send, actually I think the next slide first makes it a little clearer. So all it takes then to create a new account is get the reference, the object reference to the class account manager, which in this case is, I've just written as BBBB, but it's a publicly known, globally known permanent OID, object ID. And you send a message to that account that says, make me account. And then you have a new account, and then the only other piece there is you want to know what the object ID of the account you created is so that you can send messages to it. And so you log that, and then you can go retrieve it. And you then have your own account. And obviously you can do this as many times as you want. I don't think I do the tail because that's an obvious. So next slide. So that's literally all it takes to create an account. There's other details, obviously, I'm just the high-level viewpoint of it, but essentially it's send a message, get an account. So let's go talk about doing something next. So how about I want to do something simple like transfer coins? And we already know that a base class account is where the main SagaCoin balance is maintained. So next slide. So in the header, I'm doing a standard header again, and the current account, in this case, I'm going to introduce the cur account, CURACCT variable, which is, again, a global, something managed by SagaPython. And its value is defined in the header here for the account, in this case, AAA, arbitrary number. And then the rest of these values are arbitrary. If you think about the way, like take Bitcoin, for example, if you hand out your public key to receive coins in a UTXO, literally anybody can send it to you. There's nothing stopping, in fact, it's very common. Businesses will put out a single public key, send your money to that public key. Not so great for anonymity, then you want to generate different public keys, but there's nothing stopping you. If you look at the regular banking world, if you have the routing number and account number of a bank, somebody's account, you can send money to them. You can't draw it, but you certainly can send money to it. So there's no verification on the receiver is the point. So we follow that same model for the very simplest transfer. I'll show three-party in a second. Next slide, please. So we're going to do the exact same thing. We're going to take coin from our current account and send it to a new account. The only difference is we need to know the object ID of it, and so the first line creates an object reference, class obj var, of the account, a target account we want to send to. Then all we're doing from here is taking the coins out of the first account and putting them in the second. So we draw the account, we draw the coins out with a very simple take command, and NNN would be the number of coins that we're sending. And then if there's an error, remember that if there's an error, no object state changed. So if the transaction fails and you look at the object state database, your coins will still be there. And then afterwards, you simply put it. You send the message to the target account, and it puts it in there. And again, if there's an error, you'll be able to error exit out. Literally that easy. Remember that because these are all objects that inherit from classes, those calls could be doing, you could override and inherit them and do all sorts of things with them. Next slide, please. Let's go do creating a class. So that's all great. I can send messages to classes and accounts, all that type of thing. How do I create a class? So one of the first rules is that classes can only be created in transaction scripts. And what that means is that if you had method code in a class, even though theoretically they could do the same code, you're not allowed to create a class from within a method of a class. The reason for that is strictly security. I believe that there's ways to create malware doing that. If I'm wrong, we'll increase that over time. Okay, next slide. How am I doing on slides? Oh, man. So I have about 13, 14 slides left. I think I should be okay. Maybe, if not. So the key point, so let's walk through this code from the left side first. Remember I mentioned a decorator? In Python, if you were normally just creating a class, you could do it without, the first line here, Saga class is the decorator. You would do it without a decorator, and you would put, you would open parentheses after, in this case, the word class asset, and you would put the arguments into that for creating the class. In our environment, what we did is, because this is really a SagaPython CMI class, you don't put it there at all. There's no inheritance on those classes inside of Python itself. The inheritance is actually part of the CMI. And to do that, we simply move all the parameters up to the decorator. So you put the decorator Saga class, you give it a list, one or more of the base classes that inherit from. In this case, it's just called class Saga class. You can give it a meta class. You could give it an account, and the other variables are in the previous thing where I covered what a decorator looks like. After that, the code looks the same. Another really interesting piece is that the class asset, the word class asset, CLS asset, is actually only local to the transaction script Remember, we're dealing with object IDs. So the class has an object ID, not a name. This does not create a name, it just allows you to use it inside the script better. The next field down would be fields that are referenceable over the CMI. So again, a class and the class manager infrastructure consists of methods and fields. That's the actual interface to it. Then you'd be defined somewhere. This is where they're defined. You define the fields with the Saga field table, and then if you were to initialize them, you would use the same command which is right below it, which is underscore init, double underscore with parameters that you're initializing it with. One thing below that, though, in the self assignments, if those variables were actually in the field table, they get assigned into the state for visible to other classes. If the variable names do not exist in the fields, they're actually local variables to that class for object instances that are only visible within Python code within CMI methods. It takes a little while to get used to, but it's considered global variables to the objects, local to the class manager infrastructure object instances. I don't know how to explain it better yet. We'll work on that. Going down the next level, to define a CMI method is nothing more than putting the Saga method decorator above a regular method. And after that, your code should look exactly the same, and you should not be aware at this point when you're writing the code that you're actually writing code that is being called through the class manager infrastructure. It looks like you're calling regular Python code. In this case, I'm doing this is class asset, so it has some sort of count, some sort of value. And in fact, I called it call count. If you see in the init, it says self.callCount equals 0. And so I can increment or decrement it, so it could represent any number of instances of an object. Excuse me. If you're looking down the right side, you need to be able to eventually return the object ID. So once you've created the class, which is what happens by the last call, the call count function, that's the last piece of the class. After the code's rolled over that, the class actually exists locally. It still hasn't been written persistently to the object state database because the transaction hasn't completed yet. When it does, the class will be written out and globally managed. But until then, you still want the object ID to be able to reference it, so you ask the new class for its object ID. That's classAsset.oid, and then you log the object ID so you can use it later. Farther down, you've now created the class. Let's go use it. So you use the exact same thing as above. It's a class. You create the reference to it with a class obj variable. And then in this case, you might want to make a new instance of a class. So you call that variable with the new command with the parameters that you defined in the class init function, which again looks almost identical to the way Python works, with the major difference being that the parentheses have to be there. And then, of course, as you can see the rest, you can log that object's instance as well. You can insert it into your current account and maintain the persistence for it. Technically, it's possible to create objects that are only alive for the transaction script. You can actually pass them around, and when the transaction script finishes, they will actually eventually go away. Not 100% sure what to do with that yet, but it's technically there. Next slide. Okay, so what I showed earlier was how to send coins from one account to another. And, we're just scratching the surface of capabilities, and I pointed out that, in fact, there's no verification on the receiver whatsoever. So, if I was a criminal and I wanted to incriminate somebody, I could send a whole bunch of money to their account and then say, see, they're part of our, ring to, blackmail the mafia, I don't know. So let's not do that. So next slide is how to do a custodial transfer. So on the basic idea, custodial transfer isn't very difficult. If you think about Coinbase, for example, they own all your private keys, so they can generate all the transactions they feel like between them, and in fact, they can actually, ahead of time, verify the transactions offline and then drop them in which they do a lot of that. Wouldn't it be nice if we can do that as a generalized solution? And the third-party concept does just that. So what happens is your third party is something that, sending and receiving party generates a new public and private key, either for their, directly for their account object or a sub-object of that, one of its child objects. And it hands those private keys to a third party, an orchestrating party. Third party then can write its own transaction script that involves those two other parties, as long as it can sign for them and prove that it has their private keys. So all it needs to be able to do is generate signatures for those parties in whatever code, whatever they agreed upon to do an operation between them. And then the last piece of doing that is, how do you prove that the third party is who they are? Well, they sign it with their own key as well. There's a interesting bullet at the end on the bottom one, which has to do with performance. If I have a third party doing a transaction between accounts A and B, and the same third party happens to be doing a transaction between, say, accounts C and D, and those two transaction scripts don't interact with each other, you can actually do those in parallel as well. So I don't have to even serialize as like if I was a CEX. I can do a lot of things in parallel, because it's the whole point of capacity of doing parallel chains is kind of our thing, you know. Okay. Next slide, please. So this is getting actually into the source code, but these are all comments. The key point here is that when the third party is generating the transaction, it's using the SPSubmit tool to add the private signatures into the transaction itself, and I'll show that in a minute. If you look down at the three comments from the bottom, you notice that I'm actually, very, very original names: from accounts to account, from account signature to account signature. And the objective is to be able to prove all these signatures out in a transaction script, so that you can verify at that point, that the receiver, not just the sender, has agreed to receive the data. Next slide, please. By the way, how am I doing time-wise?
5:36 p.m.
I know. When does it shut down? 6? Oh, good. I'm going to make it easy. Good. Skip around, no problem. Speed it up a little bit. So let's just go through the source of the transaction script for a third party. The first part is very identical to any other one. You put a header together. Nothing particularly special there. The only important point, though, is this is a third-party accounts header, and that's their account, not either of the two parties involved in the transfer. Okay, let's go to the next slide. And here's the source code to be able to do it. So remember that the submit tool is generating the from account and to account variables with the object ID. You could just easily hard code these, but there's no reason why you can't pass them in as well. So here I am passing in the from account and the to account and generating object references by creating instances of class object var. Excuse me. And then I'm doing the same thing as I was before. I'm taking coins from one account and putting them in the other, but in this case, I'm adding in the signature, and that's literally just a key field, keyword field, in the method to call, in this case, take, and I'm saying the amount I want to take, and the NNN, the number, the amount that it is, and the signature to prove that I can take it from it. Because right now that message is being sent from the third-party account to the first to the from account party. So you can't just say, oh, well, I can just do that openly, because that means anybody can write a transaction to say, hey, I'll take all your money out and send it somewhere else. So that's the whole point of having these signatures. And again, if there's an error, the thing logs out and logs the error. And then on the put side is exactly the same thing, only again, the signature is being verified. Now, if you compare that to the earlier one, what I was showing is that a given account that you've already, it's your account and you've signed it, is sending unverified to some receiving account. Okay? In that case, the receiver, of course, doesn't have any control over receiving the money. They go, oh, great, I got some more money for free. But you're guaranteed that the source is a valid signature, valid account. And internally, the CMI is taking care of this, actually looking up the caller to make sure it's a valid call. In other words, to take that one step further, if you were to try to, say, call a take on an account, and obviously any other type of method, and you didn't have the signature for it, when it went to look for it, it would say, no, I'm not going to allow you to do that. But it's also going to check that the calling transaction, the calling account, had also signed as a valid transaction as well. Okay, this is actually going to work fine. I'm actually going to come out almost right on time. So let's go look at just a little bit about how this happens behind the curtain. So the objective here is hopefully I've convinced people that they're going to write basically Python code in a object state database model on a distributed blockchain that shards, and the account model enables you to scale with capacity of nodes. That was the objective. If we've got there, great. If not, I'll keep trying to get there. So this slide should read, this should be the blue slide? Yep. So let's go take a quick look behind it. And by quick, I think it's really quick. Let me see. Yeah, it's kind of quick. Good. So next slide. So the way this works behind the scenes is that the class objvar instance actually is nothing more the object ID with a reference to a stub. So there's a second object called a stub object that's dynamically generated, because again, we can compile and run anything we feel like. We can also write the code dynamically and execute it, and that's what we do here. And then we dispatch that code through the CMI library, and then there's definitely a typo. The next slide should read dynamic skeleton generator, not stub generator. It goes from stub to skeleton, so we'll fix that when we put the slides up. And then it dispatches the code. Well, that's really great. How does it know how to do this? But remember that the classes are objects in the blockchain too. So remember that we can go look at it, CMI can go look at those classes to decide what the interface should look like, because the methods and the fields are actually defined. So that means that when you're making a method call on an object reference, it's actually going out looking at the type, looking at the object instance, and then the types, the classes of that, and the inheritance of that, and using that to define what the methods and fields should be, and using that to bundle it up as a stub that can be sent over the CMI library to a skeleton that unbundles it based again on the same information about the methods and fields and distributes them. So again, on the bottom left is the actual extra piece. So you do all that, but how do you execute the code? Same place, the class has the interface and the code, so you go back to the class, you get the method code, you compile the method code, and you execute it. Now, that may sound like it's fairly slow, but if you think about it, most of the code that you're going to use regularly is going to be repetitive. So any node that's written well, and ours will do this, will simply cache the compiled code. So in fact, you won't actually, those steps there won't actually exist. Just say, okay, I know what method is, call that code immediately, and it'll be compiled code. Next slide. So that's all great. How do we do that? So what I listed is a handful of pieces that we need to use to be able to pull it off. And hang on, I just need to do something here. Right. So the really interesting thing about Python is we originally thought we were going to modify the compiler and modify C code. Well, Python is a very, very well-evolved language, and in fact, there's almost nothing you can't do to Python in Python. So it turns out that we don't need to, we literally are just writing all Python code in the background to make SagaPython work. Some of the utilities that we're using, one of them is called a callable, and that's defined as the underscore call method. And what that means is that when you call an object instance of a class, Python class we're talking about now, instead of just executing internal Python code and having it do whatever model it feels like, you can actually have it call your code, and you can do whatever you feel like and return anything, and the code will run normally. And we actually leverage that because, I'll show you in a minute, but in the stub, it looks like you're making a call directly from the class obj var. You're actually creating another object, returning it, and calling that instead. The next part is for any reference. So all of the what's called the dot notation or the dot operator for, and Python uses the same operator as everything from C++ to Java, is object name, dot, method, or field. And in the method would be arguments, and field would be either read or write it. What Python allows you to do is, even though you're using that syntax and it looks like that's what you're doing, there's a function called getAttribute. And so instead of actually doing the operation, it calls this function. And then you can make it do anything you feel like. So when you think you're calling a method, in our case, you're not actually calling the method, it's actually bundling it up and sending it over to the CMI. The nice part about that, it's completely transparent to your code. You never have to worry about it. We already covered the class decorators. Internal Viewpoint, how are we actually making the class decorator manage the class? Turns out that in addition to all the other features of Python, it also has full introspection. And what that means is it'll compile the class code, literally the thing that says class, and compile all that code and then hand it to the decorator, when you can then ask for all the source and all sorts of information about it. And that's how we use that to then generate the interface in the CMI version viewpoint of the object itself. So it's, again, from your point of view, you didn't see any of it. We will, of course, all this source code, everything we're going to do is open source, of course, so you will be able to see all of how it's working. But in terms of writing your code, you don't have to care about it. One of the other interesting pieces is comparing importing versus inheriting. So remember I said that you have modules in that Python modules, and I might want to be able to use all sorts of library Python module code. Well, problem with that is I don't want to read anything local off of a node, so I can't depend on any environment in a node operation. In other words, I can't, other than some standard things that we can define, if you create a new module and you want to be able to use it, you need some way to import it. So what we did is we overrode the entire import system of Python so that modules can be imported, but they're only importable if they're in the object state database as what's called class module instances. At the same time, because Python uses these two variables, metapath and path, as how it goes about doing the importing, we can actually completely block off so that you don't import anything else from a URL or anywhere else, so you don't basically import malware to your system. So we have is a completely controlled environment. And next slide. We've already mentioned this, and I'm a little bit repetitive, but the The bytecode interpreter is actually a C function, and it's a long loop. You can go look it up. It's in cevent.c if anybody wants to ever look it up. All we're doing to that is adding a counter into it, essentially, and that's basically all you need. And of course, if the counter goes beyond whatever the total gas units that you've passed in, then the thing stops and you return an error. As I just mentioned, we can disable all of the dangerous parts of importing, which, all of this is really nice because we're not actually modifying the underlying Python environment at all, we're just using it. We are, to be clear, we're using it in a way that's completely non-standard and you wouldn't expect Python to do it, but we are just basically using Python. And then, of course, the last line there is we pull out anything that would talk to a local operating system, so you can't do things like, kick off random programs and send malware around the world. Next slide. Let's walk through, again, this is all just the internals. It's not stuff you have to care about. How do you go about doing the class obj var that we've talked about, and how do you internally turn it into a stub? Well, you use what's called a callable. So the class obj var itself has a call function in it, so that instances of it call that function with the syntax. That's why I say you have to have the parentheses syntax to force the call. And then internally, that returns a separate object. So it looks like you're actually doing a call with the class obj var instance. You're actually not. Its entire job is nothing more to return a different object, which then takes in the dot syntax for the method or field. So now you have a stub object that's receiving a method or field call. That object is part of a class that includes the getAttribute function, which forces those operations to actually go to the getAttribute function instead of directly to the method or field. And then the getAttribute function actually sends it over the CMI and then returns the result. Your code never sees any of that, but it looks like you're sending a local call. The only other piece here, as I put at the bottom, is if there's a way to do it, I'm sure somebody in the Python world can describe how to do it without parentheses. We haven't stumbled onto it yet. Next slide. So the skeleton model. So you receive the message. The CMI has told you what method to call, what object to call, and it's going to do the call from the, it's going to do a call on an object and pass what's called a self variable. In object-oriented programming, when you call a method, you pass in the object instance, which is known as self normally. It can be any variable name, but by default, everybody calls it self. So here's an interesting problem. You're actually calling from a skeleton, which is not the object that you're actually operating on. And inside that object, it's going to go then use the self to make self calls in access variables internally as well. Remember that those have to go through the CMI. So what you do is, instead of actually passing the self variable to the object instance, to the methods for that object instance for the class, you actually lie to the class. You send it the self of the skeleton. It won't know the difference because they're all objects. And then when it goes to do any sort of operation, which should be a local call, use the same getAttribute trick, and it actually calls the getAttribute function in the skeleton, which then decides whether or not it needs to read a CMI method, talk to a local Python method, or call another ancestor class, or whatever else you're doing with it. So the only other piece is, technically, when you're doing the self in our environment, you have to put the parentheses in front of it. You don't actually have to do that. We're doing that to stay consistent with the calling of messages everywhere. It just makes more sense to make less mistakes that way. And next slide. So in the example source code, which is online, there's a prototype showing how the transaction script is actually executed. and how those separate functions, the header, the body, and the tail, are executed. What this is I excerpt a few pieces out of it to just be able to walk through what it actually does. In this case, you're reading in the script on the first line, so you're taking the script, you're writing it into a temporary file, and then you're reading it in because Python likes to read in from a temporary file, and you're then passing it to the compile command, and that's just a built-in command of Python, and it returns back a compiled object. Hasn't executed it yet, but it's returned it back. Now you have an interesting thing. I have a compiled piece of code, but I haven't run any code through it yet. So for example, if it's a class that doesn't exist yet. So what I can do is exec it, which you'll see on the top right. And what that does is it walks through the code and takes the compiled code and creates what's called a module out of it. Then a little bit farther down, now that I have body function, this is doing a body, so I have my wrapper, my body function, which is an internal piece you don't have to worry about. I have my body code, which is the part that you wrote. And you'll notice an exec line that simply says exec it and pass it globals. Presto, you just, oh, I'm sorry, I've got that wrong. Go down one more. If you look at the eval command, which makes correct, you call the eval command calls a wrapper function, the wrapper function calls your body function, the body function does the code it's supposed to do, and presto, you just created your classes or did your transfer or whatever you want out of it. This is literally what the execution application is doing. Again, the prototype of it you can see in our examples online. And getting to source code examples, and then I think this is the last slide. Yay. Okay, so if you go to xbomb.io and register for access to this, you'll be able to see two things. One of them is this list of source code. There's a body test example. Pretty much everything that's in the slide deck is in here. A lot more detail on how the transaction execution works, except I think that I misspelled it. It's actually called SagaPython.py, not SagaPython transaction.py. Also, if anybody's interested, historically, we did a proof of concept a year and a half ago using just straight Go code, not Python code, with single inheritance, and there's examples of that as well. That's all written in Go. And presto, you have an entire system that scales with a account negotiation capability, and all you're writing is Python code. Thank you very much. I think
Okay, so we're going to change pace a little bit right now. I didn't want to kind of trample over Dave's anything. He's done a really great job giving a good background into kind of the technical aspects of the chain, how you're going to get started with it. What my role as Chief Product Officer here is around kind of bridging the gap between the technical that we're going to go build and the real world use cases and how you're actually going to make the apps and make it come live for you guys. One of the things that we are super focused on is ensuring that this isn't just for, it's not just for the cash, it's not just for the game, it's not just for the fun of it. This has to have purpose. So we wanted to build a technology that really solves real world application and not just creates a big stir, a big thing, a big marketing thing. We're going to deliver real-world benefits to those in kind of the fintech and crypto applications, just as much as in the industrial space, automotive, any sort of heavy regularized industries. We're going to build out a chain tech that is going to be enabling you to map out the real world onto the blockchain, and not just kind of having to go through smart contracts and all of those things that just make life difficult, frankly, to be able to create the things that will make the enablement, to make the technology worthwhile. So if we go on to the next chart, so well, technology fails me. Cool. Bear with me a second so I can keep up with the pace of things. Okay. So when we rethink through what it is that we're trying to achieve, we look at the big challenges that are happening, okay? And how do we reinvent those things? How do we ensure that we are in the strictest and most controlled environments? How do we innovate in those spaces to ensure that we can help solve, break some of those hurdles down, and ensure that life just becomes a little bit easier? I come from a background of 20 plus years in sort of heavy, deep industrial domains, and 9 times out of 10, the technology is the easy part. The people and the process are what kills it. And one of the blockers to introducing new technology in is that the people are not ready to adopt it. And for the large part, it's regulation. Because the regulation doesn't match the way they want to run the process, which doesn't match the technology capabilities that are available to them. If we can bring that easy button to those companies in a way they haven't seen before, we can help smooth the way. We can help match the processes. We can help match the way they need to do things and ensure that the regularized industries actually have a new way of working. They can kind of break some of those barriers down because they know that the content that we're creating here, the audit trail and the genealogy that we have within the actual product itself, delivers what they need in order to satisfy their regulation. We need to become that underlying foundation for all global transactions, be it fintech or be it industrial. Doesn't matter. We're just building a capability, a framework upon which anybody can build. And you would have just seen with Dave's discussion, it's an open technology, it's an easy technology. We're not sort of creating anything particularly new here. We want to make that easy for people to consume and start developing on. You know, if nothing else, walking away from the session today and the discussions we've all had over these days of consensus is it's open, it's ready, get started, get going, learn it, and start building. And let's start discussing how you can leverage what we have here to make everybody's everyday life easier. If we go on to the next chart, when we look at reinventing things, we want to identify the blockers to progress. How do we revolutionize those industries that we all know and love, aviation, automotive, pharmaceutical? They all have their own challenges. You see it in the press every day. Supply chain issues are the bugbear of just about every company trying to build anything, especially in today's world. You look at pharmaceutical and medical trials, the level of fixing and fraud that goes into the data that is in the background of those kind of trials, we can't ignore that any longer. We have to find a way to be able to fix those underlying problems so that us as a society can grow and so that people can start to trust the information that's been put out there. And that's the only way we're all going to grow together. So how are we going to do that? By crafting that developer experience. This is why the ecosystems, the alliances, the partnerships play that we're sort of having as part of our Prasaga initiative is super important. We want developers to be part of the family. We want to have partners and alliance groups who just want to work with us because they all have the same vision that we do, that we can work collaboratively together to build the next generation of blockchain and not be stuck in the way of the previous way of working, which frankly is just limiting. We're going to provide that ecosystem. We're going to set everything all up so everybody can succeed. We're going to make sure that everybody who wants to be part of the developer program has everything at their disposal to enable success. And if you don't see it, talk to us. We'll get it enabled for you. If you need training in some area, talk to us. We'll find a way of training you. Whatever anybody needs, we'll make sure that the teams are distributed and in the right places to enable everybody who wants to build on this as a collaborative token, frankly. I've got a little video at the end here just to give a bit of a flavor of kind of the sorts of things that we've done before. This is one of our earlier pieces of work that we've done. It was for the hackathon we ran about a year ago, which is around the automotive space. And this is really before even the stuff that you've seen that Dave presented today even was in any of the form you've seen today. This is our initial ideas, and we wanted to put something together which showcased the flow, the kind of the idea that we have. Yes, it's in automotive, rip and replace to any other industry, and you can basically reuse the same kind of constructs. Do you want to run the video for me, guys?
There was a problem statement that was put in from Bosch Engineering and Business Systems, and it was specifically how can they accomplish capabilities with a blockchain for automotive supply chain. And what they were really looking for in the final analysis was auditing of the entire supply chain for the end customer, for the dealer, for the manufacturers, and all the way down for visibility into the raw material supplier. And ensure that the metal that was used in order to make the screw that's in the motor mount on your car complies with the specifications necessary for it to be in there, right? So all of these things, which aren't really available today, what we came up with and what we actually created was a full digital thread, which is another thing that manufacturing and industry has really been looking for, that they have a holistic view of the entire supply chain, all of the parts that are integrated within any one product or device itself. So this is what the outcome was. Now it's not complete because it was for a hackathon and we got so far. All the code to do all of the functions is there and it's available as open source for anybody to look at and play with, but it's not necessarily implemented within this. And I'll talk through some of the functions that aren't implemented and you'll be able to grasp how they are. So the first thing is this would be the view of the dealer. And as you see, they have not gotten any cars yet from their upstream suppliers, Ford or GM, and they haven't sold any cars, so there's no downstream. A couple of things here. This right here, this number here, you'll see on every single item that you view, and each one is globally unique and will never be repeated. And this is very important because this establishes the ability to have all 7 billion people in every single entity, organization in the world to have their own unique 256-bit string of random alphanumeric characters that will never be repeated. So that is your identity, almost like your social security number, the VIN number on your car. All of these different things are now represented in a 256-bit string and are part of your account. So anything that you own would be a subset of your overall account unique ID. There's 2 buttons that do work on here, and one of them is new part. What that is that is a fungible asset, as we call them. There are no tokens necessary within this system, because you can actually move possession of an item from one account to another account. We eliminate smart contracts by implementing this extensible blockchain object model, or as people are starting to understand now, a global operating system. So new part is a fungible asset. That means that we can fractionalize it. We can make a batch of them, 10,000 parts or something, and we can fractionalize that and separate them and move them to different accounts. And a non-fungible asset would be one where there's only one unique item. And although new assembly is built from a fungible asset, in actuality it becomes a non-fungible asset. In this case, in this instance, an assembly, the final assembly would be the vehicle, the car. And there will only be one number associated with that car. However, all of the parts, an assembly can be made up of assemblies, Assembly can be made up of parts, right? It depends on, there may be somebody that's actually assembling the engine that GM is putting in the car, right? So that would be an assembly in an assembly. So that, though, turns out to be a non-fungible token, basically, or in the we call a non-fungible asset, because the car itself will be just that one unique identification number, just like your VIN number. It's replacing basically the VIN number on your vehicle, just digitally. So I can go into any one of these different accounts, and as you see now, we're in Ford's, again, unique ID. Now we see a much more a broader view, because the upstream suppliers for Ford, and in the Bosch problem statement, it said 3 suppliers and do 3 parts each. So it won't be a fast car. In fact, it'll be you carrying a wiper blade, a steering wheel, and a spark plug as you're walking down the street. But in the digital world, this is a car. In the metaverse, right? And then downstream, as you see now, there is a customer here because of the fact that the dealer is a customer of the OEM, of the manufacturer itself. The dealer does not have any customers because they haven't bought a car from Ford yet and haven't moved it down. Now, if we go into any one of these accounts and the supplier, again, you see no upstream suppliers. They have rubber trees in their backyard and they mine all their own metal. However, you see the assemblies and the parts that they do have in their inventory, which is available right now for Ford or GM in order to purchase. Again, as I stated, new parts are fungible assets. And so there's, say, 10,000 wiper blades in this batch. All 10,000 of those wiper blades will always be referenced back to this ID number. So you always know which batch it came from, and that will never be confused with wiper blades that ever came out of another batch. And any of the upstream suppliers that have a certificate, say for the composition of the rubber in the blades, the metal or the ceramics, whatever used in the spark plugs, each of those things, that number will always be associated with this number batch. It would be showing here, and you would see it going all the way through. Now, say that GM or Ford, they wipe out the wiper blades. What you do now is they go ahead and they make 10,000 more wiper blades. Now they have a physical asset or a physical piece that they need to add into inventory and make it available for GM and Ford. All you do is hit new part. And I can go in now and I can do new wiper blades and whatever this is. Now realize, even though this is an automotive supply chain demo, this could be a cosmetic supply chain, pharma supply chain. We don't care what you call these things, right? What we're giving you is the underlying code to make that asset in the blockchain, but you're defining what that asset is. You'll never write a smart contract again, don't have to. And what you do is just create part. You would have a certificate, your SKU, whatever you want in there, but this could also be a bank, and this can be an account, and it can be all of the assets or all the transactions that ever happened between you and the bank. But this time it's immutable on the blockchain, right? I don't have to call the bank anymore and say, what are these different charges from, right? Because they associate completely through. We're the foundation in order to do this, but you would just create part, and now that would have a new part, and they would have a new wiper blade listing and a new 256-bit hash for that batch of wiper blades. You can really start to imagine what you can do with individuals and with businesses on here, and what it gives you as far as the overall ownership or the possession of your assets and your life. And every transaction you ever did belongs to you and nobody else.
As you can see, that was a relatively simplistic demo. We spent a couple weeks building that out alongside the hackathon itself. It's really to show the power that's enabled through the SagaChain that we have here. The innate ability to be able to map real-world objects directly in the way you model it in the blockchain itself, how you construct your accounts, and the hierarchy of things that go to make an account or are owned by an account, just entirely simplified. Then spread that ability to be able to then do everything you need from a transaction purpose in parallel and not have to serialize everything. Suddenly life becomes quicker, it becomes simpler, okay? one of the things that, this is just super simple. This is from the manufacturing side. So what? Who cares? Okay, well, let's think about the problem statement here. One of the issues associated with today's world is a lack of traceability of raw materials, parts, sub-assemblies that go to make vehicles. Let's keep with that as an idea here. A vehicle recall today can take anywhere from 6 to 12 months to complete the paperwork, to identify the vehicles that are involved. It costs millions of dollars for companies to be able to pull all that together purely to solve what is a problem in production, and then to ensure that we can, using the regulatory bodies, recall the vehicles, fix what's needed. If everything is all stored and available through the blockchain, that becomes a super quick query of a few minutes to pull the data and then construct that report of these are the vehicles that are impacted by this particular issue. Now I can go and solve that problem in days and weeks and not months and years. Millions and billions of dollars are going to be saved out of that industry alone through having that capability. Switch that into pretty much every other industry that follows the same sort of suit. Aviation, same problem space. We talked about the pharma trials and the faking of the data. Again, you can solve that through this kind of technology, putting it onto the chain, have the traceability. This is where this is our priority. And, this is what we think about on a daily basis, is how do we make that solution available to all. Just wanted to give you guys a quick overview of kind of, our vision, our future. This is where, as a product, this is what we want to try to see the world changed because of. If you guys are interested in learning more or have ideas or, want to have a conversation about any of this, come and have a chat. We're here till 11 p.m. Contact us on all the social networks and have a conversation. Cool. Thanks, guys.